is Professor Michael Crommie. So he's Professor of Physics at the University of California at Berkeley. So Michael really is one of the pioneers of scanning tunneling and microscopy-based characterization of material surfaces. He received his Bachelor of Science from UCLA in '84 and his PhD from UC Berkeley in '91. He was then a postdoc at IBM, Almaden, for 2 years, becoming assistant professor at Boston. And then he moved his lab over to Berkeley in 1999. Michael has received multiple awards and honors, including a National Science Foundation Young Investigator Award, the AAAS Newton Cleveland Prize, the Slow Foundation Fellowship, and several more. His research interests are to explore the local electronic, magnetic, and mechanical properties of atomic and molecular structures and surfaces. And in fact, Michael was one of the first people ever to move individual atoms on surfaces. He created the famous quantum corral, which is now covered in pretty much every textbook on nanoscale physics. And I saw it's also your profile picture. So more recently, he has been investigating the electronic structure of 2D and topological materials, including 2D topological insulators and highly correlated 2D electronic phases. In that context, his talk today will be on imaging spin-ons in a 2D gapless quantum spin liquid. Okay, thanks, Michael.
Okay, well, thank you. I just want to say that my image is, see it there, that's actually a relativistic quantum corral made of Dirac fermions, so it's not the old one was non-relativistic. So, okay, so today I'm, let's see, I'm gonna, oh, oops, I'm sorry, okay, there I am. I'm gonna tell you about some measurements that we performed that provide evidence for quantum spin liquid behavior in single layer 1T TASE2. Let's see, I'm sorry, having some problems with the computer here. Okay, and so here's an outline for my talk. First, I'll say some introductory words about quantum spin liquids, and then I'll talk about single layer 1T TSC2, and I'll show you how, I'll introduce you to this material, and I'll show you how it satisfies the requirements of a quantum spin liquid, namely that it has a frustrated spin lattice, it's a Mott insulator, and it has local magnetic moments. Then I'll show you some data, and I'll show you how we've been able to observe what we believe is quantum spin liquid behavior in single layer 1T TSE2. Namely, we've been observing long wavelength modulations that we believe are due to a spin-on Fermi surface instability, namely spin-on quantum interference. So let's start with this question: what is a quantum spin liquid? First, the key ingredient is that you need a frustrated spin lattice, and a frustrated spin lattice is basically a triangle. If I have a spin lattice where the spins are interacting via Heisenberg Hamiltonian, like what you see here, and if I put that on a triangle, then you can see that if they're antiferromagnetically coupled, then that third spin doesn't know which way to point. So that's frustration, magnetic frustration. And there's a number of famous magnetically frustrated lattices, such as the triangular-lattice and the Kagome lattice. Oh, by the way, can you see my cursor as I move it around? Can you see it?
Yeah.
Okay, great. And so these frustrated lattices, classically, if you have classical spins, they have lots of low-lying states. And quantum mechanically, they also are quite interesting, and they can exhibit quantum spin liquid behavior. So what is a quantum spin liquid? First, I'll just say that quantum spin liquids are highly entangled quantum systems. And I think it's useful to first ask, what is not a quantum spin liquid? For example, this spin lattice I'm showing you here in this picture is not a quantum spin liquid. It's a Néel state, 120 degrees rotated antiferromagnet. All the spins are fixed, and so this system is not entangled. I could write it as a product state of all those spin wave functions. It has magnetic order. And if I look at any particular site, the average spin on any one site, on any one lattice site, is not zero. So that means it's not a quantum spin liquid. On the other hand, if I look at this state down below, what I have here is the famous resonating valence bond state that was invented by Phil Anderson back in the early 70s. what you have is a bunch of coupled singlets states on this triangular lattice written in this funny way. It's a superposition. And now this is a quantum spin liquid. As you can, when you look at it, you can see that it's a highly entangled state. I cannot write it as a simple product state. There's no magnetic order. And if I look at any particular lattice site, the average spin on that lattice site is 0. So that's a quantum spin liquid. Now, one of the special things about quantum spin liquids is that they exhibit charged fractionalization. And what that means is that if you stick an electron into a quantum spin liquid, then it will have to break up into the natural excitations of the quantum spin liquid are neutral spinons, which have spin 1/2, and spinless charge-ons. And so as you can see in this little cartoon. And so one way to sort of think of that intuitively is like, consider this resonating valence bond state that I show down here below. And if I pluck out an electron, then I leave behind an unpaired spin and a holon, a hull. Now those two, the holon here and the spinon, they can migrate away. If you start rearranging the bonds and moving electrons around, you can sort of see how they separate and move away. And that's a way of thinking that the electron is breaking apart into these two other types of particles. Now, there's a lot of different types of quantum spin liquids that people have been studying lately. Here I show a list of different materials where people have claimed to observe quantum spin liquid behavior. There's a whole bunch of them. And there's a whole bunch of different types of lattices that people have seen them on, and also different symmetries, such as the U1 gauge symmetry, Z2 symmetry, and also some of the quantum spin liquids are gapped, some are not gapped, some have edge states, some don't. So there's a whole zoo of quantum spin liquids that people have been discussing recently. But today, for this talk, I just want to focus on one particular quantum spin liquid, and that's this one that I've circled, and that's a triangular, a quantum spin liquid on a triangular lattice with U1 gauge symmetry and a gap, and it's a gapless state. And there are several materials where people claim to have seen this type of behavior. And so okay, so let's take a closer look at the quantum spin liquid that might exist on a triangular lattice that has this characteristic. And so to think about like where it might come from, a nice place to start is the Hubbard model. So let's consider this triangular lattice and let's fill it with electrons so it's half filled, 1 electron per site. And then we can describe the behavior of the electrons with the Hubbard model. So I have T, the hopping parameter that tells me how the electrons hop from site to site, that gives a bandwidth. I have U, which is the Coulomb repulsion between 2 electrons on the same site. Now, if the U value, the Coulomb repulsion is really huge, if I crank it up really high, so that's a lot bigger than T, the hopping parameter, then this complicated Hubbard Hamiltonian reduces to the simpler Heisenberg Hamiltonian that I show down here. And the ground state for this Hamiltonian is the Néel order, the 120-degree rotated Néel order, and that is not a quantum spin liquid. On the other hand, if I reduce the gap, if I reduce the Hubbard gap, make it smaller, so it's still bigger than T, but not too much bigger, then what happens is there's going to be more interactions. I can think of more higher order terms in the perturbation expansion. And so that leads to more interactions. And in particular, you can get this interaction called a ring interaction, where you have these 4 adjacent spins are all interacting according to this little formula down here, and that creates additional frustration, and then that allows a quantum spin liquid to occur. So this additional frustration then can lead to quantum spin liquid behavior on the triangular lattice. And so if you have a quantum spin liquid on the triangular lattice, then we expect electrons to fractionalize into spinless charge-ons and neutral spin-ons. The charge-ons are gapped. Because in order to create a charge-on, you have to supply enough energy to overcome the Mott insulator energy gap. So they're gapped out, but the spin-ons are not. The spin-ons are free to move around, like free electrons. So, but they're neutral. They have no charge, but they're free to move around. And because they're fermions, they fill up a band up to a Fermi level. So they have a Fermi level. So you can think of them as like a neutral metal. They just swim around like electrons in a free electron gas, but they have no charge. And so they have a Fermi surface. Here you can see the Fermi surface. And here, this is the Brillouin zone, this hexagon, and the B1 and B2 are the reciprocal lattice vectors of the lattice. And there's one additional nuance to this picture, which is that the spin-ons are neutral, so they have no charge, but within this quantum spin liquid, they can feel each other. They act as though they have charge. They have something called a gauge charge, which occurs due to the U1 symmetry of the Hamiltonian, which creates emergent gauge interactions. So they act as though they're charged. So two spin-ons will repel each other, and they will create electric fields and magnetic fields according to Maxwell's equations. But this charge can only be felt within the quantum spin liquid. We cannot couple to it from outside. So it's really a very strange kind of behavior. A very new kind of system, and it's hard to observe. How do you actually detect these spin-ons, these neutral objects that have this funny behavior? we cannot use familiar techniques such as electrical conductivity because they have no charge. On the other hand, you could see their behavior from thermal measurements like heat capacity and thermal conductivity, and people have done that. So here you can see some data where people have measure these thermal properties and claim to see the quantum spin liquid behavior. Also using inelastic neutron scattering, you can see the excitations of spin-ons. And so people have papers where they claim to have observed this type of behavior. But one of the quantities that's hard to observe is the Fermi surface. It's hard to map the Fermi surface of the spin-ons because we cannot use familiar techniques such as Shubnikov-de Haas-Van Alphen effect. We cannot do that because there's no charge to the spin-ons. And so today what I want to do is tell you about a new technique that we can use to observe the spin-on Fermi surface, which is scanning tunneling microscopy. And to understand that, how that works, let's first consider STM tunneling into a conventional material, just a normal material. And here, if I put a voltage on an STM tip, then electrons tunnel from the tip into the material, and the rate at which they tunnel is proportional to the wave function of the electrons on the surface of the material. That's the local density of states. And that's the famous Tursoff and Hammond interpretation of STM, which is something that all STM people know and love. But if I have a quantum spin liquid, things are different because now if I try to tunnel an electron into the quantum spin liquid, it has to break up into a charge on and a spin on. And so now the rate of which the electrons tunnel in is going to be proportional to the product of these two different particles have wave functions. And so the rate at which the electrons tunnel is going to be proportional to the product of the spin on wave function times the charge on wave function squared. Because these two things have to happen at the same time, so the probability is going to be the product. And what that means is that, for example, if the spin-on wave function has fluctuations in it, density modulations, then by measuring the tunnel current as I move across a quantum spin liquid, I should be able to see that because the rate of electrons tunneling in is going to be dependent on the spin-on wave function. So you might wonder, why aren't there a bunch of papers on this from STM people? You know, why aren't people publishing papers right and left on spin-ons? And the reason, of course, is because quantum spin liquids exist in a Mott insulator. It's an insulating system. And so you can't do STM on an insulator because they got to get the charge out. And if it's insulating, it doesn't work. You need a conducting surface. And so it turns out that a trick that you can do is that if you have a single layer, a two-dimensional quantum spin liquid, then you can tunnel into it, because now if I have a two-dimensional quantum spin liquid, then I can tunnel electrons in, they break up into spin-ons and charge-ons, but then I can drain them through a conducting substrate. If I put my two-dimensional quantum spin liquid on a conducting substrate, then in principle, I could observe the quantum spin liquid behavior. But this two-dimensional quantum spin liquid it's very special. You need a very special material to give you a two-dimensional quantum spin liquid. For example, the minimum criteria that it must satisfy is it has to have a frustrated lattice, it has to be a two-dimensional Mott insulator, and it has to have localized spins. And so what I want to do now is introduce you to this relatively new material, single layer 1T TSC2, which we believe satisfies these three criteria and which actually gives us a quantum spin liquid. So here you can see the top view of this material. It's a transition metal dichalcogonide. And here this view, you see the purple balls are the tantalum, and the greenish balls are the selenium atoms. And if you look at it from the side, it has the familiar TMD, transition metal dichalcogonide structure, which is a tri-layer. You have the selenium layer on top, the tantalum layer in the middle, selenium layer on the bottom. Each selenium atom sucks 2 electrons out of the tantalum, and so the tantalum atom has +4 charge, and there's only 1 d electron in each tantalum atom. So that's kind of nice and simple, and those are the electrons that count. Those are the ones we care about. But there's one other nuance to this, which is the fact that electron-photon coupling in this material causes it to form a charge density wave. So there's this really funky charge density wave where it's called a Star of David CDW, where the CDW supercell is this Star of David. And this is due to electron-photon coupling, and you can actually calculate this with the density functional theory. And so the lattice that we care about is this triangular lattice of the CDW. So that's the important lattice for this problem. And so as you can see, that's a triangular lattice. So this material does satisfy this first criteria of a frustrated lattice. But is it a 2-dimensional Mott insulator? That's a trickier question to answer. And one of the reasons why that question is hard to answer is because, for example, if you look at the bulk material of TaSe2, 1T TaSe2, it's a metal, and that's about as far from a Mott insulator as you can get. And so here it is. You can see that it's a metal. But on the other hand, what surface science people have done is by looking at this material by STM and ARPAS, people have shown that at the surface it behaves like an insulator. So that's good. That's a little bit more like what we want. But the situation is kind of complex, and the reason it's complex is because of interlayer coupling. Here, interlayer coupling, in my opinion, is the enemy. That's the problem with this material that makes it complicated and hard to understand. There's another material, the sister material is 1T TaS2, where you replace the selenium with sulfur. And this material is even more famous than TaSe2 because this material in bulk is an insulator. And you can see evidence for that here in this. This is STM spectroscopy done by, I think this is Yayu Wang's group who did this a while ago. And you can see the nice lower Hubbard band and upper Hubbard band and a nice energy gap. So this material is an insulator, and most people believe it's a Mott insulator, although even that is controversial. And this material has been predicted to be a quantum spin liquid by Patrick Lee and coworkers. And in fact, over the last few years, there has been some evidence for gapless quantum spin liquid behavior in this material, but there's also been some evidence against it. So there's some controversy here. And once again, in my opinion, the problem is the interlayer coupling of the bulk material that really complicates things. And so an obvious thing to do is to get rid of the interlayer coupling by going to the single layer limit. And so that's what we did. That was our goal here, is to go to the single layer limit to get rid of that interlayer coupling. Now, actually, the material I wanted to study was 1T TaS2, but my MBE growers wouldn't grow it because they hate sulfur. MBE guys hate sulfur, but they love selenium, and so they grew 1T TA. They said they won't give us TaS2, but they'll give us TaSe2. So that's what we studied. And so we used MBE to grow our samples because MBE is a nice way to grow very clean samples, good for STM and surface science measurements. And so our samples were grown by collaboration with Ziek Shen's group at Stanford and Sungkwan Mo's group at the Advanced Light Source. Sungkwan Mo is a beamline scientist at the Advanced Light Source in Berkeley. So they grew the material using MBE. And basically, they took a wafer of silicon carbide, they heated it up in UHV to grow bilayer graphene, and then they used evaporators to grow the 1T TaSe2 on top in a monolayer form. And then they gave the sample to my group to look at with STM. And here you can see an STM image, a typical STM image of this material. So this is a big island. On the edges, you see the single layer, the monolayer 1T TaSe2, and in the center, the white part is the bilayer 1T TaSe2, and the dark blue is the bilayer graphene. Now, if you zoom in on the monolayer part, then this is a STM image of the single layer 1T TaSe2, and each of these blobs in this image is a Star of David. It's hard to see the atoms. There's 13 atoms in each of those blobs. With STM, it's hard to see the atoms, but if you want to see the atoms, then what you do is you put a carbon monoxide molecule on your tip and you perform non-contact AFM, and that's what we did. And when you do that, you can see the atoms just fine. So here they are. These are the atoms that we measure with CO, carbon monoxide tip, non-contact AFM. And these are the selenium atoms, and they're pretty much where you expect them to be. So it all kind of looks kosher and good. And here I show the spectroscopy, the STM spectroscopy that we measure on this material. And so this is the STM spectroscopy of the single-layer 1T-TSE2, and it's an insulator. So it has a nice energy gap of about 110 millielectron volts. We have this, here we have the valence band, the conduction band. So it's a nice insulator, but the question in our mind is it a band insulator or a Mott insulator? And that's not completely obvious. So let's think about it for a moment. So let's consider, for example, the unit cell of this material. Now, the unit cell is the CDW unit cell, and there's 13 atoms, 13 tantalum atoms. Each of them has 1 d electron. So we have an odd number of d electrons. So you might think, well, it should be a metal, you know, by normal solid state physics reasoning. And in fact, if you do a density functional theory calculation on this material, which our theoretical colleagues did, here they're listed in the lower left corner, then they indeed do see a metal when you do DFT. And here's the band structure, the DFT band structure of this material. And you see there's a bunch of spaghetti here. And the way to interpret it is here you have 12 atoms that I've shaded in red here. Those outer 12 atoms have 12 electrons, and those 12 electrons occupy 6 tantalum bands here in this red band. So this spaghetti here, those tantalum bands are filled with electrons from these outer atoms. This flat band filled. So that means it's a metal. Oh, can you hear me? It says my internet is unstable. Can you hear me? Hello, can you hear me okay?
It was just unstable for a few seconds, just the last sentence or two.
Okay. So the most important atom is this one in the center, because all the other bands are filled except this atom in the center donates its electron to this flat band. So that flat band is half filled. It's a metal according to DFT. But if you look at it a little closer, you'll notice that the width, that's a very flat band. And so the width of that band is only on the order of 20 millivolts, whereas the U, the Coulomb repulsion that you expect in that band is on the order of 2 electron volts. That means that this ratio is really tiny, much less than 1, like on the order of 1/100. And so that means that correlation effects must be very important here. And so we expect this to be a Mott insulator. So that's strong evidence that this is a Mott insulator. And so we would like to understand it better, but a problem that we have is that there is no accepted theory for performing ab initio calculations on a Mott insulator. And so in order to get some sense of the electronic structure of this material, we decided to make a very rough approximation to just, which other groups have done as well, to give us a sense of the physics. And so we decided to do DFT plus U in order to model this material. That's only a very rough approximation for this material, but we did it anyways to help us out. And when you perform a DFT plus U calculation on this material, where you choose a U of 2 electron volts, which is commonly accepted for this material, then you do in fact get an insulator. A gap opens up, as you see here in this band structure down below. And when you plot the density of states from this DFT plus U calculation, you see that it actually looks pretty reasonably close to what we see experimentally. Maybe even better than you would expect. So you get this lower Hubbard band here, this peak, and you have the upper Hubbard band here. And if we actually look at the wave function from the DFT plus U, it also matches the experiment pretty good in the lower Hubbard band. Here on the bottom, you see the wave function, the theoretical wave function of the lower Hubbard band. And here up top, you see the experimental wave function that we measure by doing DIDV mapping of the lower Hubbard band. And they match pretty good. You get a lot of state density at the center of the Star of David. However, if we look at higher energy, if we go into the upper Hubbard band right here, then we see that the match is very bad. Now the theory and the experiment do not match. And that's not a surprise, because this is a Mott insulator after all. It has strong correlations, and the correlation effects are messing up the match. And basically what you see is that in the experiment, we have a depletion of local density of states in the center, whereas in the theory, you have a lot of local density of states in the center. And now if we look at slightly higher energy, once again, the theory and experiment don't match. Whereas in the theory, we have a depletion of local density of states in the center, but in the experiment, we have lots of local density of states in the center. That's exactly opposite behavior. And what's going on, what we believe is going on, is that there's an electron localized in the center of the Star of David. And so when we try to add another electron into the upper Hubbard band, the state density gets pushed to higher energy. And that is not captured in the DFT, but that's what's happening experimentally. And so basically what's happening is that the correlation effect is basically kind of splitting the upper Hubbard band a little bit. And so the bottom line here is that we have a Mott insulator, but it's not a completely generic Mott insulator. We have this funky behavior where the upper Hubbard band splits a little bit. But that means that we have 2 out of 3 of these criteria are satisfied by our material. But what about the local spins? Do we have spins? Well, to answer that question, we decided to use the Kondo effect to see if we could detect spin behavior in our system. And so I'll just remind you what the Kondo effect is. The Kondo effect is what you get when you have a local moment in contact with the metal, in which case the spin of the local moment interacts with the spin of the itinerant electron with this exchange coupling, and that causes a many-body singlet to form, where essentially you can think of the local moment as capturing an electron from the metal, which then screens the local moment. It's actually a many-body screening cloud. And the characteristic of this many-body screening cloud is that you get a Kondo resonance in the local density of states at 0 energy. And that resonance can be a Fano resonance, where it can be either a peak or a dip, depending on details. And here we were able to observe this many years ago in my group, looking at cobalt atoms on gold. But now let's consider what happens if I put a Mott insulator on a metal. So now you might, now you still might expect the local spins of the Mott insulator to interact with the itinerant spins of the metal, but you also have the interaction between the spins in the Mott insulator. So if the Kondo interaction overwhelms the interspin interaction of the Mott insulator, then you might expect that the Kondo effect will win, and then each of these spins will be screened by the metal. And so that's a very sort of intuitive picture. But if you do actually a more sophisticated, detailed calculation using dynamical mean field theory, then it's been predicted that this is precisely what should happen. So this is a theoretical prediction that was made back in 2008 by Helms and coworkers, where they actually predicted what happens when a metal is on a Mott insulator. And they predicted basically what I just said to you. Here from the prediction, you can see that if you go into the metal, you get this nice continuous density of states. But as you go into the Mott insulator, you start getting this Kondo peak, which is due to the Kondo effect. And then if you go deeper into the Mott insulator, then you just get the Mott gap. So that's a prediction. And so we decided to use this technique to see if we have local moments in our Mott insulator. So we put our material, which we believe is a Mott insulator, 1T TSE2 onto 1H TASE2, which is a good metal. And the reason why we did that instead of just looking at 1T TSE2 on the graphene is because the density of states of 1H TSE2 is bigger, because the Kondo temperature is too low if we put 1T TSE2 on bilayer graphene. But on 1H TSE2, we're going to get a higher Kondo temperature. And so so we adjusted our growth parameters to get this kind of a material. And so here you can see it in the STM image. In this STM image, you can see a patch of single layer 1T TSE2, a patch of single layer 1H TSE2, and then here you can see a patch where I have 1T TSE2 on top of the 1H TSE2. Now, when you zoom in on these materials, if you zoom in on the 1H TSE2, then what you see is this very familiar 3x3 charge density wave, which is known to live on 1H TSE2. And if you do STM spectroscopy, then you see a nice metallic density of states. There's a little dip, but it's a nice metal. And we published a paper on this a couple years ago. You see down here in the lower left corner. Now, if you go on the 1T TS2, then you see the familiar Star of David CDW, and if you zoom in, you see the familiar Mott insulating gap, which I was just telling you about. But now, if you go on the 1T TSE2 sitting on top of the 1H TSE2, then you see the Mott insulate. You see the Star of David CDW, But if you zoom in and do some STM spectroscopy, then the electronic structure is completely different from either of the ones I just told you about, because we see a sharp, narrow resonance at zero, at the Fermi level. And here you can zoom in, you can see that, and we believe that that's a Kondo resonance. And this Kondo resonance we see all over the surface on every star of David. We see it. Now, to test whether it's a Kondo resonance, we change the temperature, because Kondo resonances have a very characteristic temperature dependence. You expect the width to increase according to this characteristic equation that I showed down here. And that's been seen by our group a long time ago, and other groups have seen it as well in the last 20 years. And so we measured the width, and we can see that it widened, as you see here. And when we plot the width as a function of temperature for this Kondo resonance, we see that it follows very closely this expected Kondo behavior for a Kondo temperature of about 60 degrees Kelvin. And here the width, the thermal, we have already done thermal deconvolution. So if the width was not increasing, we would expect it just to be flat. If there is no Kondo temperature, we would have expected just flat behavior, but instead it rose. So this is good evidence, in our opinion, that we have the Kondo effect and that we have local moments in this material. So now we see that this material satisfies all of these criteria. We get a frustrated lattice, a 2D Mott insulator, and localized spins. And so now we're ready to go searching for quantum spin liquid behavior. We've satisfied all of these criteria. And so to search for signatures of the quantum spin liquid, then what we did was very careful DIDV maps at different energies in our material. And so we took the 1T TSE2 and we put it back onto the graphene. So we got rid of the 1H TSE2. We don't need it anymore. It served its purpose. So now we're back to the 1T TSE2 on graphene. And here I show DIDV images both at very low energy and very high energy. And when you look at them, you see basically the only periodicity, the main periodicity that you see is the Star of David CDW periodicity. And if you take a Fourier transform of these images, then you really get nice peaks here at the reciprocal lattice vectors of the CDW. So that's the only real well-defined periodicity that we see. But now let's look at energies closer to the Hubbard band. So let's move into the Hubbard band. And when we do that, let's first go to this part right here, what I call UHB2, the upper Hubbard band, the higher energy part of the upper Hubbard band. And now you can see from the DIDV image that at this energy, the local density of states looks totally different. You look at these two images, they don't look the same. At the upper Hubbard band, we see lots of these long wavelength features. You can see it with your eye. And it looks pretty disordered, but when you do a Fourier transform, you see that there are some well-defined periodicities living inside of this image. And you can see them here. I've circled them in blue. If you take the Fourier transform of this image, you get these new periodicities. I call them ICS. That stands for incommensurate superstructure or incommensurate structure. Because they're incommensurate with the charge density wave. And so they appear, we get these Fourier peaks at these very specific periodicities. And if we go now, let's go to another energy, this upper Hubbard band 1 here, the lower energy part. And again, if we do the Fourier transform, we see those peaks once again. So we see these new peaks. They're long wavelength. They have long wavelength because they're inside the Brillouin zone. They're much longer wavelength than the CDW peaks. And now let's go to the lower Hubbard band, and we still see them in the lower Hubbard band. We see the ICS peaks, but now we see some new peaks that are sitting at the K points of the Brillouin zone. We call that CS commensurate structure because at those points, the structure is commensurate with the CDW. Let's take a closer look at it. And so here I show that in this little cartoon, I'm showing you this ICS structure, this blue dot. That's what. Oh, it said my internet was unstable. I'm sorry. So this blue dot here is the experimental ICS feature that we see experimentally. I just drew it here in this cartoon, but here below you can see that's what we measure experimentally. So there's no theory yet. This is just experiment. It's at 0.241 times B1 plus B2, where these B's, those Remember, those are the reciprocal lattices, the reciprocal lattice vectors of the CDW of the lattice. And so let's take a look at the energy dependence of this new ICS feature. Here's the Fourier transform amplitude of this peak as a function of energy, and we can see that it has its highest amplitude here near the Hubbard band, near the Hubbard band edges. So in this region of the Hubbard band, in the Hubbard band region, we see that this Fourier transform amplitude is really high, but as we move to lower and higher energy, it falls off dramatically. So it's really localized mainly in this Hubbard band region. It has a strong energy dependence. So when we saw this behavior, we were really mystified because we'd never seen anything like this before. And we didn't know what it was. And so we wanted to make sure that there wasn't anything funny happening on that particular substrate, you know, the graphene on silicon carbide. So we did the whole experiment all over again on a different substrate. We grew the material on graphite and we did the whole experiment again and we saw the same thing. So that's good. So that means that it's not really due to the substrate. Even on two different substrates, we see the same behavior. Here's a 1T TSE2 on graphite, HOPG, and you can still see these ICS features in the Fourier transform. But in addition, on the graphite, we saw another feature. We saw another long periodicity, which occurred at the M points of the Brillouin zone. I'm circling them in purple. And so we call that feature Q sub M. That's the wave vector Q sub M. So that's another periodicity that we saw for this material on graphite. Okay, so that's basically, you know, our experimental observation. And so in our mind, the question was, what the heck are these long wavelength modulations? Well, what do they do to us? Really strange. Where are they coming from? What is causing these long wavelength ICS, QICS and QM modulations? It wasn't obvious to us at all. Now, the answer, of course, is that we believe now that it's due to the spin-on quantum interference. But before we can jump to this very exotic explanation, we have to rule out the more conventional explanations. And so let's first ask what does not explain these periodicities. So so the question is, can we explain these periodicities with conventional explanations? And in the end, we'll show that you cannot, or at least we believe that you cannot. And so let's start with maybe the most obvious conventional explanation, at least, you know, for some people, which would be quasi-particle interference. Now, quasi-particle interference occurs when you have a system where you can have electron scattering between two energy conserving states. And then like I show here in this little diagram, and then that leads to quasi-particle interference patterns that have a wave vector equal to this scattering wave vector. So the scattering wave vector then you get a quantum interference pattern at that wave vector. And so you can calculate these quasi-particle interference patterns for different materials. And so our theory collaborators calculated the QPI pattern that you would expect for 1T TSE2 using the DFT plus U band structure. And so here you can see that if you go for example, near the Mott, near the Hubbard band edge, then you really don't have any features that would lead to periodicities at these QICS and QM. There's really no features there. There's no features in the electronic structure, at least no obvious features that would lead to that QPI. And so we think that that's evidence that QPI is not causing this. So the next obvious thing that you ask yourself is, well, maybe it's a Moire pattern. You know, maybe there's a Moire pattern that we're seeing. Well, it turns out that if you consider all the possible Moire patterns for 1T TSE2 on top of graphene, then it doesn't work. You know, you don't get the right periodicity. You can't, if you do the little twisty trick and calculate the Moire patterns, you don't get the right periodicity. So it doesn't work. But then you might think, well, in silicon carbide, you have all these weird reconstructions, you know, I forget what it's called, root 6 by root 6. You have some strange reconstructions between the graphene and the silicon carbide, which might cause it, but that's why we did graphite. Graphite does not have those weird reconstructions. And once again, we see the QICS. So we think that this is strong evidence that it's not a Moire pattern. So then you might say to yourself, well, maybe it's strain or a charge density wave. Maybe that's what it is. But there's evidence against that as well, because, for example, we do not see these periodicities in LEAD, low energy electron diffraction, but we do see the Star of David very strongly in the LEAD. So structural modifications we should see in the LEAD pattern, but we don't see this in the lead pattern. That argues against the structural explanation. Also, there's a strong energy dependence. We see these patterns at the Hubbard band, but as you move away from the Hubbard band, they die off quickly. Whereas the Star of David, we see strongly at every energy. So the structural modification, you expect not to have a strong energy dependence. Also, we did experiments at a slightly higher temperature, 77 Kelvin, and the QICS went away. Whereas the Star of David is still there, and the difference in strain between 5 Kelvin and 77 Kelvin is not so strong. So if it's a strain effect, you would expect it to still be there, but it disappeared. So that argues against a strain origin. Also, MBE of van der Waals materials tend to be very low strain systems in general. So this is, in our opinion, very strong evidence against a conventional strain CDW explanation. So what does that leave us then? So what could be explaining this? Well, the only thing that we can think of that explains it is quantum interference on a spin-on Fermi surface. It turns out that if you ask yourself, what do you expect to see for a spin-on Fermi surface on a triangular lattice, then basically what you expect to see is precisely what we have seen. And so let me walk you through that. So let's consider what happens when you tunnel the electron into the quantum spin liquid. You can see the electron, as I said before, it has to break up into a spin-on and a charge-on. And so the tunnel rate is going to be the product of these two wave functions. And so that means that if I tunnel the electron if I have a voltage on my STM tip, that means that the electron has a total energy of E times V, the total energy, and that energy has to be shared between the spin-on and the charge-on because they both appear when the electron tunnels in. So both of them have to get that energy. So what that means then is that if I bias my STM tip so that I'm tunneling electrons into the band edge of the Mott insulator, then what happens is all of the energy has to go into the charge-on because it requires that much energy to create a charge-on because you have to overcome the gap energy. So if you're right at the edge of the gap, all your energy has to go into the charge-on, and that leaves nothing left for the spin-on. But the spin-on is still there, so that means that you have to have a zero energy spin-on. Now, zero energy for the spin-ons is the Fermi surface. So that means that if I'm tunneling electrons right into the band edge of the Hubbard band, then that means I'm probing the Fermi surface of the spin-ons. And so then I can image the spin-on Fermi surface by taking images at the Hubbard band edge. So that's the idea. So then we have to ask ourselves, what should it look like? What should the Fermi surface look like for a spin-on Fermi surface in a triangular lattice? Well, it turns out that this question has been addressed by theorists. There are predictions out there, and the predictions were made by Patrick Lee's group a couple of years ago. They did some calculations using density matrix renormalization group theory on a triangular lattice, and their goal was to model the behavior of 1T TAS2. But it turns out that the material parameters of 1T TASE2 are pretty similar. And so those theoretical results should also apply to 1T TASE2. And so what they predicted using their DMRG calculations, they predicted that indeed this material should be a quantum spin liquid that has a gapless spin-on Fermi surface. And they predicted that the Fermi wave vector of that spin-on Fermi surface should be 0.375 B, where B is the reciprocal lattice vector of the charge density wave, the main lattice reciprocal lattice vector. And they also predicted something else. They calculated the spin susceptibility of this system using their DMRG, and they calculated that the spin susceptibility should have a peak at 2 kF, at wave vectors of 2 kF. Now, that is not surprising because whenever you have a Fermi surface, you always get peaks in the susceptibility at 2 kF. That's like a famous solid state physics thing. But what was strange is that there were certain wave vectors where they were unable to see a peak. So at these very special wave vectors, there was no peak in the susceptibility in the gamma M direction. And so the one reason or one hypothesis for why that's happening is that the spin-on Fermi surface is gapped in these particular directions. So it should look like this. You see how I gapped it. Now, that's not so crazy because we often see partially gapped Fermi surfaces in solid state physics for electrons, at least. For many charge density wave systems, you have partially gapped Fermi surfaces. And so that is the implication of this calculation, is that we should have a partially gapped spin-on Fermi surface where it's gapped in these particular directions, according to their prediction from a couple of years ago. And so you can ask what might cause this partial gapping, and there's several possibilities. For example, you could have a spin-on density wave, or you could have a spin-on spin density wave, or you could have a spin-on pair density wave. It turns out that all three of these possibilities lead to the same answer for the STM. But we believe that the spin-on pair density wave is the most likely explanation. So I'm going to walk you through the spin-on pair density wave and explain how this can explain our experimental results. So how does a spin-on pair density wave occur in this material, and how might it actually explain what we see experimentally? So basically, first you have to understand what a pair density wave is. A pair density wave is basically a Cooper pair that has finite momentum. The idea is that in a superconductor, you usually have the plus and minus k that creates the Cooper pair. But for a pair density wave, they're both pointing in the same direction. And so the idea of a spin-on pair density wave is basically we have spin-on Cooper pairs with finite momentum. And so the idea is that these two electrons here, or these two spin-ons, are going to pair up and form a Cooper pair. And so you might, in a superconductor, it's electron-phonon interaction that binds the electrons together. But you might ask, what's going to bind spin-ons together in a quantum spin liquid? And it turns out that it's the emergent gauge field that can bind them together. And so the idea is that if you have two spin-ons moving in the same direction, then you can think of one of them as creating a magnetic field, like a current, like a wire of current. And then the other one feels that magnetic field, and then they are attracted. And you can see that more easily by just thinking of these spin-ons as wires passing current through. And you know from introductory physics that if I have two parallel wires with current flowing in the same direction, they attract each other. And that's called Amperian coupling. And this has actually been predicted in a couple of papers. Here I show two of them by different groups. So this is something that's actually been predicted theoretically. And so this attraction could then cause these two spin-ons to form a pair density wave. And if they form the pair density wave, then what happens is that the momentum is now twice as big. So the momentum of the pair density wave is 2kF because there's two spin-ons there. And so that's a pretty big momentum, and it takes you right out of the first Brillouin zone like this. But we can fold the pair density wave back into the Brillouin zone by simply adding a reciprocal lattice vector of the CDW superlattice, of the CDW lattice. And so if we fold back into the Brillouin zone, then we get this little vector, this little red vector called P. That stands for primary, and that's the crystal momentum of the pair density wave in the Brillouin zone. But this happens simultaneously for all 6 directions. And so we expect that the pair density wave should then have components from all 6 of these directions due to coupling via scattering from defects and also scattering from spin-ons. And so this is what we expect the wave function to look like of the pair density wave. And so we can then ask, what do we expect the state density of the pair density wave to look like? And so we just square that. And if we square it, then we get these second harmonics, these blue dots. And so this is really, I'm not doing any fancy math here. I'm just squaring these vectors. So you could do this in 5 minutes with a pad and pencil. And so you get these blue dots, and it leads to a very specific prediction that you should get density waves at these very specific wave vectors, which here I'll call QICS and QM. These are then the predicted wave vectors, and this all comes from the density matrix renormalization group theory that predicted this Fermi wave vector. So it all comes from that. And so what we can do then, but the problem is that we don't actually see the pair density wave, because when we tunnel electrons in, we're only creating a single spin-on, not 2 spin-ons. But you have to remember that there's still some ungapped spin-on Fermi surface left, and these spin-ons are going to scatter off of the pair density wave density because of the gauge interaction, and so they're going to scatter, and so they're going to reflect the wave vector of the pair density wave because of quantum interference. So we'll get scattering within the Fermi surface of the ungapped spinons, and so that will lead to quantum interference at precisely these wave vectors of the scattering potential, the QM and the QICS, and so that leads to density waves, quantum interference density waves in the spin-on density that we should see with the STM, and that's what we believe that we're seeing. And so from this treatment, then you get very specific predictions of what wave vectors you should see in the density of the spin-on density. And here I show the predictions. So these are the predictions that you get from basically starting from the DMRG, the density matrix renormalization group theory. Then you end up with predictions that you should see spin-on density waves at precisely these wave vectors that I'm showing you here, QICS and QM. Now I will show you what we see experimentally. So these are the experimental density waves that we see. And as you can see, just by comparing them, the match is almost perfect. It's a really good match. And so there's really strong match, and we can work backwards from our data to then extract the Fermi wave vector of the spin-on Fermi surface. And what we get is 0.37 times B, which is the reciprocal lattice vector of the CDW, and we can compare that to the theoretical value of the Fermi spin-on Fermi surface, which is 0.375 B. So it's a pretty good match. And so we see that the spin-on treatment explains our data very well. And so we consider this to be very strong evidence for quantum spin liquid behavior in single layer 1T TASE2. So that's sort of my story, that's the story. And I'll just mention that it's not a perfect story. Obviously, it's not perfect. Nothing's ever perfect. There are some open questions. For example, what about the commensurate superstructure, the CS? What about these periodicities at the corners? I sort of brushed those under the rug. And the reason I sort of brushed them under the rug is because the quantum spin liquid cannot explain them. You cannot get those periodicities from a quantum spin liquid. However, a 120-degree Néel state gives you precisely those periodicities. And so we think that what's happening is that we have local fluctuations that can sometimes give us that periodicity. In fact, they do appear as patches on the surface. And so that's what we think that is. But another open question is, what about the primary vectors, those red the primary vectors of the pair density wave? Why don't we see that? If you look at the second harmonics, you also would expect to see the primary vectors, these red vectors. We do not see them, and that's a problem. Why don't we see them? We don't know. They should appear by the treatment that I just explained to you. But there are some possibilities. For example, there could be a structure factor argument that causes them to have much lower amplitude. Another possibility is that these are longer wavelength features. And so to see these longer wavelength features, because the K value is smaller, we need larger islands. So it might be just that our islands are not large enough yet to see the primary vectors. And so we're still looking for those. And another issue is, where are the spin-on Friedel oscillations? We don't see the spin-on Friedel oscillations. What we're seeing here are not Friedel oscillations, but by the same type of treatment you would expect to see the spin-on Friedel oscillations. One possibility is that the spin-on bandwidth is too small and our energy resolution is not good enough, but we're not quite sure. So that's an open question. Okay, so let's see. So so to conclude, we believe that we've measured the Fermi wave vector for gapless quantum spin liquid on a triangular lattice. For the future, there's a lot of obvious things to do. For example, to explore the spin-on Kondo effect, or electrostatic doping of quantum spin liquids, or disorder and temperature behavior. So these are things for the future. Here are my collaborators and funding agents. A lot of different institutions contributed to this, and all these, and we got funded by Department of Energy and National Science Foundation of the US. And all of these people contributed to this project, but I do want to call out a couple names. These are the people in my lab who actually took all the STM data that I've showed you. Wei Ruan led this project, and Yi Chen also was an important part of it, and Ryan Lee as well. These are the guys who took all the STM data that I've showed you today. Thank you.
Yes, thank you, Michael. That was a very, very fascinating talk. I would open the session to questions from the audience.
Here I showed the open question. So if you can't think of anything to ask me, you can ask me about this. See, tell people what to ask.
Maybe I'll start with one then. So actually at the very beginning you talked, when you talked about the Mott insulating state, I guess that is very sensitive to half filling, if I understood you correctly. So how sensitive is all of this to essentially changes in the Fermi level, say by doping or electrostatic gating and coupling to metallic substrates?
Well, that's a great question, and we'd love to measure it. You know, so quick answer is I don't know. You know, and so I mean, when you start doping a Mott insulator, all kinds of weird stuff happens. I mean, I think that's still sort of a, you know, kind of an evolving topic, and so we would like to understand that. I mean, when we make the system, it's not doped. You know, and so to dope it, we have two possibilities. We can either sprinkle impurities on top of it, or we could electrostatically gate it. Now we started to try these electrostatic gating experiments, but that's still in its infancy. And if we start sprinkling charged impurities on top, then we start creating all kinds of disorder and impurity potentials, and so it becomes a mess. You know what I'm saying? And so it's hard to answer that question. You expect, I mean, when people start doping Mott insulators, you get lots of states in the gap, and things start getting messy. Yayu Wang's group has done some nice experiments, you know, exploring that in more high TC related systems, but I think it's still sort of an open question. I don't know what more to say about that.
Okay, thanks, Michael. Any other questions from the audience? Okay, maybe if not, I'll ask another one. You had one slide where you showed the spin-on density wave patterns compared to what you expect from theory, just a couple of slides back, I think.
Here?
So you probably mentioned that, but I somehow missed it. So why are the spin-on density wave patterns different for graphene and for graphite substrates? I mean, they appear different.
We don't know. That I should have written that down as an open question also. It's good that you spotted that. I think the referee has been asking us about that too. Are you the referee? And so we're not sure. Yeah, let me think. I mean, we're just not sure why that is. That really is an open question. I mean, you know, the two systems are ever so slightly different. I mean, you have a different amount of screening on. If you look at the graphite versus the graphene on silicon carbide, you know, the graphite has more screening. And so I don't know, maybe more screening is going to reduce U. So, you know, the T over U ratio is a little bit different. And so maybe that matters. I'm just not sure, but that's a good question.
Thanks.
I actually have a question, but I don't have enough knowledge to ask about this directly. I was wondering about the relative permittivity for maybe this TMDC, like TASC2, and is there like a common relative permittivity we can use for simulations?
I'm sorry, did you say permittivity?
Yeah, because I'm using it to do some electrostatic simulations, and it's a bit hard to figure this thing out for myself.
Yeah, okay. I know, I mean, I don't have a great answer, you know, off the top of my head for that, but I do know who you could ask, you know, who could actually answer that question. I mean, you know, someone, because, you know, Stephen Louis' group at Berkeley, who has collaborated with us on a lot, you know, actually they're collaborating with us on this also. And they've done a lot of ab initio calculations in collaboration with my group. You know, we do the experiment, they do the theory. And I know that they've put a lot of effort into calculating dielectric constants and the, you know, the effective dielectric constants of different TMD systems, mainly in the context of calculating excitonic behavior, you know, because you have excitons, you have to worry about the electron holes attracting each other and all the dielectric function. And so they've put a lot of effort into that. I don't know how that all ports over to this system where we have a much smaller band gap, but I know that they've put a lot of effort into calculating the dielectric constants, the dielectric function behavior, but I don't know more details. You know, I can't give you details on it, but you might consider contacting Stephen Louis' group, or you can email me and I could introduce you to some members of their group if you want.
Yeah, thanks, Michael. I mean, the substrate sort of dielectric constant, was that or anything that you took into account when you for these DFT plus U calculations? Or I'm not too familiar with DFT plus U, to be honest. But.
No. For the DFT plus U, no. I don't think we did. No, it was just no. We just did the bare TMD and then the TMD plus U, but we did not go the extra mile to include the screening of the substrate. I guess that would have made it, significantly more difficult. I'm not sure, but no, we did not do that. I mean, part of the reason too is that the DFT plus U itself is such a, it's not so great. And so we didn't feel like it was worth putting huge amounts of effort into optimizing it because it's already only a very poor approximation of a Mott insulator.
Okay. Do we have maybe some more questions from the audience?
Maybe John Liu's students could tell me what they're working on and what quantum spin liquid they're looking at and how does that compare to this? How about can I ask questions of the audience?
Absolutely.
Who's John Liu's students? Don't hide.
Hi, Professor. Can you hear me?
Yeah.
Yeah, I'm John Lu's student, and actually we work in another material who is also predicted to be quantum spin liquid.
What material?
It's another totally different material. Okay, and I think currently the strange behavior is what we observe is the strange Kondo effect. Actually, as in your presentation, you'll see Kondo effect, but it's very similar to the Kondo effect on isolated impurity with the S equal to 1/2. But the thing is, we think we also observe a Kondo effect, but the behavior is totally different and cannot be accounted by the Kondo effect on isolated impurity. And the idea we have now is we think maybe in our system, the coupling between the magnetic moment is quite strong, and the coupling between the conduction electron and the magnetic moment is quite weak. So basically, the thing is we see the Kondo effect on a spinon system or quantum spin liquid. That's what we did.
Well, did you know that Patrick Lee has calculated that? I don't know. Are you familiar with that?
So maybe Mike, you can share the reference with us if there's been a calculation on.
I'll just show you the calculation. Here it is.
Okay.
This is the calculation. So this is the so here's a Mott layer. See that in the Hamiltonian there, and then here's the metal layer, and then you have the hybridization between them here. And so then they did some fancy, all this fancy rotor stuff, how you solve it, all this fancy physics. And then they plot this phase diagram where you're modifying, the different couplings. And you can see how that top layer, that Mott layer, sort of evolves from a metallic state into a spin liquid. And this heavy metal is sort of like a heavy fermion kind of state. Where you get like all this Kondo stuff. Yeah. And so this is so I did not include this in my talk because, I didn't have enough time to do this, but they did this theory sort of because of, our experiment. So they wanted to understand better what happens when you have a Mott insulator in contact with the metal and you start tuning those J parameters. And so they have this whole prediction. So you guys probably should read this paper.
Yeah,
Yeah, thank you very much.
This is the data, experimental data there is your data that they work with?
Yeah, they didn't, I mean, I don't think they were really trying to fit our data. I mean, this is a standalone paper, you know, we're not co-authors on this. They just pounded through, you know, the theory and just have this beautiful, you know, theoretical result. So it was motivated by our experiment. And I think that our experiment, I think, sits here at this star. I think that they're predicting that this is where we are living in our experiment is right. This circled star, I think, is where they believe our experiment is living. But but this is, you know, they calculate the whole phase diagram.
Okay, I think that's very useful. Thanks.
Okay. So now you're going to tell me what material it is? See, I gave you something.
I'll ask Lu Jung to email you. I mean, it's not my place to tell you about his experiment, but I will certainly you know, tell him to contact you.
Okay. I'm just curious. I mean, you know, I promise not to run out and, you know, and measure it.
Okay, do we have any more questions from the audience? If not, I suggest, yeah, so thank you, Michael, once again. That was really, really exciting and fascinating talk. So I can't wait to hear more about this.
Actually, one more thing. My student is telling me that the first author of that paper used to be here working with us at the C2DM. He's my colleague Vito Pereira's student, the first author on this paper.
Oh, wow.
So we know him, I guess, and I also know Inti, and so I guess we can contact them and ask them about the results.
Hey, where is Vito these days, Pereira?
He's currently in Singapore. Yeah.
So he's at the big Graphene Institute?
Well, we're somewhat in shutdown mode, so most people are working from home, but yeah.
Okay. Good. Glad to hear it. I just sort of lost contact with Vito. We published a paper a few years ago, but it's kind of, you know,
yeah.
well, that's good to hear.
I'll pass on your greetings to him as well. And
okay, thank you.
I think I was on the thesis committee for the first author, so I read his thesis.
Oh, yeah, I think he did a very nice job on this. I mean, he powered through it pretty quick.
Thanks, Mike. It was a wonderful talk. Learned a lot.
Okay, yeah, my pleasure. Thank you.
I agree. Okay, well, thank you, Michael, once more. And yeah, it would be great to be in touch. Okay.
Okay, bye-bye.
Thanks, everybody. Bye.
Bye-bye.